Assalamualaikum warahmatullahi wabarakatuh. It's a pleasure to present to you Dr. Ashadi and Dr. Farid on our project titled Design and Simulate of an Electronic Systems Block Diagram. Before we dive into the content, I would like to briefly introduce the members of our team. I will start by introducing myself. I am Nunisrinda binti Soimi and my group members are Aisyah binti Ruslan, Muhammad Salihin, Chong Yongzin, Henny Tuyan, and Nur Iza Izzati. To begin, let me outline the main content we will be covering today. So the first is introduction to the system. Next is design and operation of each block, which is contain oscillator, summing amplifier, filter, rectifier, regulator, and load. Next is simulation results and calculations. For the last is discussion and conclusion. Now, let's begin with the introduction to the system we designed. This project involved designing and simulating a complete electronic system, including oscillators, filters, a rectifier, voltage regulator, and a load. Each part was tested through simulation and worked as expected, with minor differences still within acceptable limits. The results matched theoretical calculations closely, and the system successfully delivered a stable 5 volt to the load. Overall, this project helped us understand how each component functions and how they work together in a real electronic system. This project analyzes an electronic system with the key components: two wind bridge oscillators, 1 kHz and 20 kHz, a low pass Butterworth filter, which is 8 kHz, a full bridge rectifier with a 1 microfarad filter capacitor, a voltage regulator, 5 volt output, and a 1 watt load. Each stage was studied to understand its role in generating, filtering, converting, and regulating electrical signals to power the load effectively.
Hi, my name is Nur Izzati. My metric number is B122310554, and I will explain about oscillator 1, including its function, the calculation, and the circuit with simulation result. The first oscillator generates a low frequency signal at 1 kHz for the main output path, while the second oscillator generates a high frequency signal at 20 kHz for function like filtering or switching. Each oscillator plays a specific role depending on the frequency needs of the system. For oscillator 1, its main purpose is to provide a clean and stable low frequency sine wave that will be used as the primary signal input for the next stage in our electronic system. For the calculation part, we use the wind bridge formula, F equal to 1 over 2 pi RC, and we assume both capacitors C1 and C2 to be 10 nanofarad. Based on this, we calculate the required resistor value to get 1 kHz, which gave us approximately 15.92 k ohm. Since 15.92 k ohm is not a standard resistor value, we use the closest available value, which is 16 k ohm. Then we substitute this value back into the formula, F equal to 1 over 2 pi multiplied by 16k and multiplied by 10 nanofarad. And we got a frequency of 994.72 Hz, which is very close to the target 1 kHz. This confirms that our component selection is suitable for the design. After completing the calculations, we design and simulate the oscillator circuit using the selected component values on multisim. From the simulation, the output waveform show a clean sine wave with a frequency of around 989 Hz, which is very close to our target of 1 kHz. The maximum output voltage reached approximately 14.9 volt, which makes sense since the DC supply was 15 volt. This confirmed that our design and calculation were accurate and the oscillator performed as expected in the simulation.
Assalamualaikum and selamat sejahtera. My name is Muhammad Salihin bin Hamzah. My metric card number is B0822101181. Today, I can explain about oscillator 2. The type of oscillator is wind bridge oscillator. For resonant frequency is 20 kHz. For DC supply is 15 volt. For frequency resonant, we use a formula 1 over 2 pi RC. For find the R, we use a formula 1 over 2 pi FRC. So R, we got answer 3.98 kHz, which is 4K, and for FR is 19.89 kHz, which is 20 kHz. R1 equal for R2, which is 4K. Okay, this is oscillator 2. This is a circuit for oscillator 2. And then this is output for oscillator 2. Summing amplifier. A summing amplifier use an operation amplifier to produce an output that is the sum of multiple input voltage. It's widely used in audio mixing, signal combining, and DAC. Input into the inverting terminal via resistor, allowing a equal our wide additional based on resistor value. This is summing amplifier calculation. RF equal to 20K. For Rin is 45K. For V1, 14.1 volt. For V out oscillator 1. For V2, we got a 4.58 volt for VO oscillator 2. So we use a formula VO equal to RF2 over R5 multiply V1 plus RF3 over R6 multiply V2. So input RF, Rin, V1 and V2 in formula, and we got the answer is negative 8.3 volt. This is summing amplifier circuit, and this output we got like this.
So my name is Aisha. I will present about low pass, active low pass filter. So for introduction for active low pass filter is the oscillator feeds signal into low pass filter which remove high frequency noise and allow low frequency signal to pass. This move the waveform before it reach the rectifier and voltage regulator, ensuring a more stable and clean signal for the load. So we use second order Butterworth response and cut off frequency 8 kHz. For calculation for active low pass filter, based on parameter table of Butterworth filter, R1 over R2 equal to 0.586. Assume RA is 1 kilo ohm, so RA over RB is 0.586, so RB is 1.71k. So next is assume R7 equal to R8. The same value is 500 ohm. So formula is FC 1 over 2 pi RC. So C we got 40 nanofarad. Last one, the attenuation of output signal. The formula is max dB minus dB at 8 kHz. So the max is 3.99 dB minus 0.937 dB. So we got the final answer is 3.062 dB. This is the result and output for active low pass filter. We got the result is 9.018 volt, and for bird plot we got 48 and 865 Hz and 3.99 dB. This is the sine wave output, and this is the circuit.
My name is Henny Tuyan. I will present rectifier. Introduction for rectifier is convert AC signal from the oscillator into DC, allowing current to flow in one direction. Rectifier is working with a 1 micro F capacitor. It moves ripple in the signal, ensuring a steady DC output. This step is crucial to power the load with stable, unstable voltage. This slide shows how we calculate the important value for a rectifier circuit, including the peak output voltage, load current, and ripple voltage. First, we calculate the peak output voltage from the rectifier. We take the maximum input voltage and subtract the voltage drop across two diodes. The formula is VO peak equal to Vmax minus 2V drop. We insert the value 12.7V minus 2 in bracket 0.7V equal to 11.3V. 12.7V is the peak from the AC supply. 0.7V is the forward voltage drop of a diode. Two diodes conduct at once in full wave bridge. Then we calculate the load current using Ohm's law, which is I load equal to VO divide RL. We insert the value 11.3V divide 200 ohm. We got the value 56.5 milliampere. 11.3V is the DC output after rectification. 200 ohm is the load resistance. This current will be used for ripple calculation next. For the frequency and time discharge, we determine how often the capacitor discharges in a full wave rectifier. Since the LPF output is 4.07 kHz, the rectifier frequency becomes 8.14 kHz. A full wave rectifier have twice the frequency. Time between each charge and discharge cycle is important for ripple. And then now we calculate the ripple voltage, which tell us how much the voltage fluctuates due to capacitor charging and discharging. The formula we use V ripple equal to in bracket I load times T discharge divided by C, which is capacitor. And we got the answer 3.47V. Ripple increase with higher current or longer discharge time. It decrease with a larger capacitor. This ripple value is a first estimate and may be refined based on practical measurement or additional component. In summary, we calculate the value of a peak rectifier voltage is 11.3V. The value for the load current of is 56.5 milliampere. And then the value for ripple voltage is 3.47V. This show how each state of the power supply affect the output quality. This is a full wave bridge rectifier using 4 diodes. When the AC input alternate, the diode conduct in pairs to produce a pulsating DC output.
Hi, my name is Chong Yongjin. My metric number is B122310419. I'm going to explain about voltage regulator starts from introduction. The output voltage provided by the voltage regulator is 5 volts. This is the stable voltage that is required to power the load, ensuring that the system functions correctly. The voltage regulator type is operation amplifier shunt regulator circuit. This type of voltage regulator uses an operational amplifier to regulate the voltage. The shunt configuration means the regulator maintains a constant voltage by diverting the excess current to ground, effectively shunting it away from the load when necessary. The voltage regulator ensures a stable 5-volt DC output by correcting any voltage fluctuations from the rectifier. It provides clean, consistent power to the load, preventing issues caused by over or under voltage. The purpose of this calculation is to determine the value of the load resistor that will allow the voltage regulator to deliver a stable power load of 1 volt at a 5 volt output. The information that given of the voltage output is 5 volt, the power load is 1 volt, zero voltage is 2.5 volt, and assume that R1 equals to R2, which is 1 kilo ohm. The answer that we get of the ratio of the resistor is 1. And the next equation, which is power load equals to output voltage square over the load resistor. And the load resistor we get is 25 ohm. This slide provides two calculations related to the voltage regulator circuit. And the total current flowing through the circuit is the sum of the current flowing through the load and the shunt resistor. Therefore, the total current is 260 milliampere. The resistor is needed to drop the voltage from input voltage to output voltage. The formula for calculating RS is input voltage minus output voltage over total current. And the current limiting resistor is 17.58 ohm. The second calculation is to calculate the value of R3. The Zener series resistor is used to limit the current flowing through the Zener diode, keep the breakdown mode, and ensuring proper voltage regulation. The final value of the resistor is calculated to be 500 ohm. The circuit shown is a voltage regulator using an operational amplifier in a shunt regulator configuration. The component that used in this circuit is operational amplifier, Zener diode, current limiting resistor, and 1 kilo ohm resistor and load resistor, which is 25 ohm. The output voltage shown by the multimeter reading in the simulation is measured to be 5.59 volt. This is the regulated output voltage provided by the voltage regulator circuit to the load. The expected output voltage is 5 volt based on the circuit design, but the simulation shows 5.59 volt. This slight difference may be due to the ideal assumptions made during calculation. The load is the final component that uses the regulated 5-watt DC power. It converts electrical energy into useful output like motion or data, proving that the system works effectively. Without the load, the power conversion process has no purpose. The rated power of the load is 1 volt, which means it will consume 0.2 ampere of current from the 5-volt output provided by the voltage regulator. This slide shows the calculation of the load resistor. The formula given of the power load is output voltage square over load resistor, which we get 31.25 ohm. The component that used in this circuit is input voltage to the load circuit is 5.59 volt, and the load resistor is 31.25 ohm. And the voltmeter that used in this load circuit is to measure the power consumption of the load. The wattmeter confirmed that the power consumption is 1.25 watt, indicating that the load is working properly, but with a slightly increase in power consumption due to the higher output voltage.
This shows the complete electronic system circuit, including the power supply, application state, and output load. It integrates all key components to form a working DC power system. On this on the right side, we have the power supply unit. It converts AC to DC using a bridge, rectifier, filter capacitor, and voltage regulator. The diode bridge converts AC to DC. The capacitors move the output. The LM7805 regulator output a stable 5-volt DC, powering the entire circuit with about 4.2 V as shown by the voltmeter. The wattmeter shows 705.282 milliwatt, which is the power consumed by the whole circuit. Here we see the three stages of signal amplification, likely using OP amplifier. This amplify and input analog system before sending it to the output or load. LM741 configure in amplifier mode. Coupling capacitor C1 until C5 for signal AC filtering. Feedback resistor, which is RF and RG, control gain. Biasing resistor and power rail, which is plus VCC and minus VEE. Point out that each OP amplifier stage boosts the signal strength progressively. And for the output load and indicator, the output is connected to a load, possibly an LED and voltmeter, to indicate the system is delivering power. This could, this could represent a sensor, motor, or other real-world load. And the multimeter show 4.199 volt at the output. This means the system is properly regulated and operating. Low resistor like R11 and R12 are present for current limiting. So in the conclusion, this complete circuit demonstrates how an AC input can be converted to DC, amplified, and used to power electronic component every stage, from rectification to regulation to amplification, play a crucial role in system performance.
For discussion, this project involved designing and simulating a complete electronic system with two Weinrich oscillator, summing amplifier, low pass filter, rectifier, voltage regulator, and a 1 watt load. Oscillator 1 achieved 989 Hz and oscillator 2 gave 16.7 kHz. Signal was summed and filtered effectively with negative 3.06 dB at 8 kHz. The rectifier delivered 9.34 volt DC with 3.7 volt ripple. The regulator output 5.459 volt, powering a simulate 1 volt load, deep side minus challenge with frequency, tuning ripple, and voltage stability. All issues were resolved through simulation and accurate component selection.
The conclusion is the circuit was successfully designed, calculated, and simulated to meet all specifications. Each subsystem, from the oscillator to the load, functioned correctly and aligned well with theoretical expectation. Minor deviation, such as the oscillator frequency and regulator output, remain within acceptable tolerance levels. This project not only strengthened our understanding of circuit design and system integration, but also improved our practical skills in simulation, component selection, and troubleshooting. Overall, it gave us valuable hands-on experience applying theoretical knowledge to a real-world electronic system. That's all from us. Thank you.